is there an extent to how long an alpha helix is, right? Maybe we want to take this one. There are multiple answers. Yeah, go.
If it encounters like a proline.
Why, if it encounters a proline? What is a proline known as? It's known as a helix breaker, right? Why is that?
Because it's cyclic.
Right, because of that R group that circles back on itself and constrains it. It cannot be part of an alpha helix. It is just thermodynamically not possible to find a proline in the middle of an alpha helix. Where we do find prolines very often is at the end of an alpha helix. It's a helix breaker. It puts an endpoint, it's like a book stop, on the end of the alpha helix. Once there's a proline, game's over, right? What else? What else might we find at the end of a helix? A glycine, or a leucine, or an isoleucine, right? So these stop an alpha helix, okay? Additionally, all amino acids have different propensities to form alpha helices, right? There's a table in your text that gives the propensity of any amino acid to be found in a helix. So we would find, for example, alanines in a helix very often, right? So if we have, a bunch of alanines and maybe some, let's see, aspartates maybe, right? All of these that have high propensity to form an alpha helix, then we would find an alpha helix until we start to move to a region that has low propensity of amino acids to form a helix. So there are multiple ways to break a helix. And it's important that we do, because we'll see, especially when we talk about hemoglobin and myoglobin, how big a helix is and where it is critical for that particular protein most of the time. Right, so what else about secondary structure? I know, again, people have problems with that.
Also, do beta sheets also form spontaneously the way the alpha helices do, in the sense that, like, if there are a lot of residues that have propensity to form, they just form?
They can only form spontaneously. In fact, the entire structure of a protein forms spontaneously, as a rule, right? There are, of course, exceptions. We have chaperone proteins and things like that. But as a rule, okay, protein structure arises spontaneously. It is the lowest energy state of this particular arrangement of amino acids going in this sequence in that order, okay? And that was proved by this experiment here, the Anfinsen experiment, right? I do want to get to this, and this relates to the case study that I do want to talk about, but are there any other questions? But yes, they do form spontaneously.
I have one more question.
Sure.
So, as far as the amino acids and stuff like that, do you want us to, like, memorize the descriptions of them? Like, where we can just recognize them?
It would be a good idea for you to memorize them. The exams are open notes, right? If you told me to draw a lysine, for example, I couldn't remember off the top of my head how many carbons there are in a lysine.
Just right.
But I know what it looks like, and I know that a lysine ends in an amino group, and that amino group is ionizable. It's got a pK of about 10, right? Do I care that you memorize that there's, I don't know if this is correct, 6 carbons, right? No, it might be 5 carbons, I'm not sure, right? No, okay? So you can use that for your notes, and you know, if you're taking some kind of standardized test, you might have to do that. You might have to memorize it. Do I care? No. Why? Because when I'm doing research or when I'm teaching or whatever, does it matter how many carbons are in a lysine? Absolutely not, right? And if you need to know, what do we all have? Phones, right? So, no. Okay, but what you should definitely memorize is the single letter codes.
Just about like the original J. If you, that mean it's like, can you predict the structure, you know the exact chain of what amino acid?
If you solve that problem, yes. In theory, yes. But if you solve that problem, you've just won yourself a Nobel Prize. So there are many programs that can take the sequences of a polypeptide and predict its structure. Are they 100% accurate? No. Are they better than they were 10 years ago? Yes. And why is that? Because it's the primary structure of the protein, the sequence of amino acids that determines its structure, right? So with alpha fold, for example, that's able to, you give it an amino acid sequence that gives you a pretty good approximation. Can we say for sure, you know, X-ray crystallography is now dead? because we can just predict the structure? No. There are so many weak forces happening at the same time and interacting with each other that it's very difficult computationally to do that, right? So if we look here, I'll come back to the Anfinsen experiment in just a second. If we look here, how does a protein fold, right? Well, it's actually kind of a weird process. It's not a linear process where we start with a fully, wiggly amino acid chain, and then over time we get more and more structure. No. What happens is proteins exist either pretty much entirely folded or pretty much entirely unfolded. We don't really see that much in between. And what we actually do see is that if we add, for example, we get our native protein. When I talk about native protein, that means that it's folded into its correct tertiary structure or quaternary structure or whatever. Okay, and we add a denaturant, right? And the denaturant is something like urea, something that's going to destroy the secondary and tertiary structure of a protein and the quaternary structure, but leave the primary structure alone, right? So we are denaturing it. We're taking away its native structure. What we don't see is that this native protein slowly unfolds at different regions until we eventually have a fully unfolded protein with no discernible structure at all. What we see is we add denaturant, and at some threshold, now all of a sudden, they all denature, right? So if we take a snapshot in time of what's going on in that threshold region, we see that we have either folded protein or unfolded protein. And the reason for this is this energy funnel that we see here. So at the top we have fully denatured protein. So it's just been synthesized, right? So we just willed it into existence. So we have this now denatured protein. And we begin to get nucleation sites. Meaning, for example, right, we've just made this protein here, or we just made this polypeptide here. Well, this alpha helix, because it's more stable as an alpha helix, or this region, because it's more stable as an alpha helix, will form an alpha helix. The formation of this alpha helix, right, makes it easier for nearby regions to also adopt their lowest energy state. Here, for example, a beta loop, here another alpha helix, and this acts as nucleation sites for other ones. So the more secondary structural elements we have, okay, the easier it is for the rest of the protein to adopt its structure, right? So once we get our first, right, kind of formation of one or two secondary structural elements, quickly the entire polypeptide collapses down this energy well until we arrive at the lowest energy configuration, which is the native state, right? So that's how proteins fold. It's an all or none for the most part process, right? We don't get a halfway fold protein, with an exception, right? That is our case study, right? So, all right. So let's go over Anfinsen's experiment, and then we'll get into our. Well, actually. All right, let's zoom through Anfinsen's experiment. This is important. Basically, what this experiment shows is one of the seminal experiments in biochemistry, protein structure, and it shows what I just told you before: that the primary structure, the sequence of amino acids in a polypeptide, are what determine the structure of the fully folded protein. How was that found? Well, it was found using ribonuclease. Ribonuclease is just an enzyme that breaks down RNA. Okay, they isolated it from cows, bovine ribonuclease. What's important is that they were able to measure how much active enzyme there is, because RNA is very easy to measure in terms of how much you have. So if you add active ribonuclease to a mixture of RNA, well, you can measure over time that the amount of RNA goes down. If you add inactive ribonuclease, well, then what's going to happen to the RNA? Huh? Nothing's going to happen, right? If it's inactive, it's not going to act on that RNA. We'll get to enzymology next weekend, right? So, but for now, right, just know that if it's active, it will degrade the RNA. If it's inactive, it doesn't degrade the RNA. So what he did was he inactivated it. How did he inactivate it? Well, he added a denaturant, urea, and a reducing agent, beta-mercaptoethanol. Why do we need to add beta-mercaptoethanol? Well, because the structure of ribonuclease is locked into place by, again, those disulfide bridges. Those disulfide bridges are cysteines in their oxidized state. If we reduce them, well, now they don't form that covalent bond, right? We go back to that slide, just as a refresher. If we reduce a disulfide bond, so we put 2 electrons and 2 protons back, well, now we have 2 self-hydrogens, which are now no longer covalently linked, so we've broken that disulfide bond. And that's the reducing agent beta-mercaptoethanol. So when we add both a reducing agent breaking those disulfide bonds, and then add our denaturant urea, which disrupts the hydrophobic effect, forcing the protein into the correct configuration, well, now we have denatured and reduced ribonuclease. RNA is not degraded. And what he discovered was that if he takes this denatured and reduced ribonuclease, he removes urea, and then he removes the beta-mercaptoethanol, we get back to native active ribonuclease. So he could go from here to here and back with nothing else. So there's what was found, what he discovered then, right? The point of this experiment is not that, oh, we can remake ribonuclease, that's incidental. The point of this is that there's no secret sauce in making a fully functional enzyme as long as you have the primary structure of the enzyme or protein intact. Okay, it's the structure, it's the primary structure of a protein that determines its structure, which goes back to, I think, what you asked, right? Can we predict the structure of protein just from its sequence? Well, again, in theory, yes, because that's the only thing that determines its structure. But doing so is more difficult, right? Because there are so many forces acting at the same time. All right? So before we move on to my practice problem and the case study, hopefully I might be able to pull this off. Any other questions about any of this?
I had a question from earlier. I wanted to know why amino acid is beneficial for amino acids to be a Zwitter ion.
Why is it beneficial for them to be a Zwitter ion?
Yeah.
Well, it's not that it's beneficial for them to be a Zwitter ion, right? They just are, because the pKa of the carboxyl is about 3, and the pKa of the amino group is about 8, right? And the only way that we can make a polypeptide is by having a peptide bond. For that, we need a carboxyl and an amino group. So just by virtue of them being, right, in solution, they'll always be a Zwitter ion. Now, why were alpha amino acids selected evolutionarily to be what comprises a protein? I don't know. All right. Yes.
Do you think you could explain a little bit more clearly what constitutes a glucose alpha?
Can you speak up?
Do you think you could explain a little bit more like what constitutes one turn of an alpha helix?
One turn of an alpha helix. Yeah, sure. One turn of an alpha helix is just a 360-degree rotation, right? So we start here, right? Go down one rotation, that's one turn, right? So from here to here is 3.6 residues, right? Or 5.4 angstroms, right? And how do we get that? Well, the rise is 1.5 angstroms per residue. The pitch is 3.6 residues per turn, so 3.6 times 1.5 is 5.4 angstroms vertically for every 360-degree rotation of the helix, right? So it's a pitch, just like you have a pitch on a screw, right? When you go to Home Depot or whatever, or your local hardware store, the screws come in different pitches, depending on the application. The nut and the screw have to match in pitch, right? So that's just describing how many turns per millimeter. Here we're describing how many turns per residue, or how many residues per turn. Okay, so here's an example of a question I might ask you on the exam. Okay? So let's go through this here. First question. What amino acids make up this structure? Well, first let's start easier than that. How many amino acids make up the structure? This should all be on campus. You don't have to worry about taking pictures. I uploaded it a little bit before class, so if you downloaded it last night, it's not going to be there. But don't worry about pictures right now. Just look at here. Okay, how many amino acids do you think we have? Or residues. Sorry, how many residues do we have? 3? All right, good, so 3. So, next question. What amino acids make up this structure? Right, so again, why you should more or less memorize the structure of amino acids. Okay? So what's the first thing that we should do? Huh? No, before the R groups. Find the backbone, right? Here, take this. Point out the backbone. There's a little laser thing. Don't shine in your face. Alright, so what should the backbone pattern be? Huh? N, C alpha, CO. N, C alpha, and the carbonyl option. That's what I'm calling CO. N, C alpha, CO. N, C alpha, CO. We have 2 possible starts here. We have 2 amino groups that we can see. We have the one on the left and the one on the bottom. So let's go to start the one on the left. If we start on the left, does that follow the pattern of the backbone? No, right? Because now we're just going N, C, 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 C. So that can't be. Now what if we start at the bottom? Let's start at that amino right there. To the right of where you want. No. Yeah, that, right? So we start that one. N, C alpha, CO, N, C alpha, CO, N, C alpha.
Oh, wait. Is it?
Oh, no, yeah, you're right. Sorry.
Okay. I thought it was true.
Very good. So now we have our backbone. So we have a C alpha here, a C alpha here, and a C alpha here. Okay? So now we just have to look at what the R groups. Now we can look at the R groups. What are the R groups connected to this, to the C alpha? And in what order are we going to say them? Right? So now we've said our backbone is over here. Right? This is our backbone. Are we going to talk about this protein or this polypeptide in this direction or in this direction? First direction or second direction? First, right? N into C. Very good. So what's the first R group? Well, that's just a methyl. Okay, so what amino acid has an R group that's just a methyl? Alanine, exactly, right? So there's our first amino acid, alanine. What's the single letter code for alanine?
A.
That's an easy one. Very good. Let's keep going. What's the next one? Right? C alpha, CO, and C alpha, CO, right? So here then, we have our R group. What R group looks like that? Lysine, right? What's the single letter code for lysine? K. Right? Let's keep going. C alpha, CO, and C alpha, CO, right? So here's our last R group. So what residue is that?
Histidine.
Histidine. What's the single letter code for histidine? H. That's another easy one. AKH. AKH describes this entire structure, right? Now, okay, so now, what's the one letter code for this? Now, what is the charge on this structure at pH 4? Right? What is the charge on this structure at pH 4? This one is going to be tricky. And it involves stuff that we learned on Tuesday and stuff that we learned today. Right? So let me draw this just kind of abstractly. We have N, C alpha, CO, and C alpha, CO, and C alpha, CO minus, and plus. Right? We have our alanine. We have our lysine, and we have our histidine, right? So, how do we tell what the charge on this structure is going to be at any given pH? What do we need to know? pK, right? let's first identify all of the ionizable protons that we possibly have. Well, we always have the N-terminus, right? The N-terminus is always ionizable. What about this carbonyl? Well, when it was a lone amino acid, we did have an ionizable proton there. But when we are now part of a peptide bond, no longer ionizable. And the same is true for the amino groups. Once we have the carbonyl carbon now, and the amino nitrogen, those are no longer ionizable. So we don't have any ionizable groups here, and we don't have any ionizable groups here either, right? But we do have an ionizable group over here at the end, okay? An ionizable proton. Does the methyl group on alanine have an ionizable proton? No. What about on lysine? Yes, it ends in an amino group. Amino groups are ionizable. What is the pKa for the lysine side chain? I'm actually asking because I don't have memorized. That was too many. It's only one number. Thank you. 10.4. Somebody said high. Okay. All right, so that's good. Now we come over here to the histidine. Well, that one I do have memorized. So that one's 6. This terminal carboxyl, let's just call it 3.1. And this terminal amino, let's call it 8.0. All right, so now what we can do is let's draw this at, say, pH 0, 1 molar HCl, pH 0, okay? What's going to be, forget about the charge, what's going to be the protonation state of this tripeptide? Will the amino group be protonated at pH 0? Yes. Will the amino group on the lysine be protonated? Yes. Will the amino group on the histidine be protonated? Yes. Will the amino group on the carboxyl be protonated? Yes, right? So at low pH, the lowest that we can imagine, everything will be protonated, right? So we'll say this is protonated H3N+, this is protonated COOH, this is protonated ANH+, and this is protonated NH3+. So what's the overall charge here, right? Well, we have a +1, +2, +3, and a 0. So we have a total charge of +3, right? Now, let's start increasing the pH. As we increase the pH past the first pKa, 3.1, okay? So that's the first pKa that we hit. What does that mean for this proton here? Remember the Henderson-Hasselbalch equation? A minus over HA equals 10 up to the pH minus pKa. So if pH equals pKa, then A minus equals HA, right? We went over this on Tuesday. So when we hit pH 3.1, we'll have equal amounts this and equal amounts that, yes? Now if we keep increasing the pH beyond 3.1, which one will we have? This or COOH? This one, right? So now what's the charge on this one? Well, we have +1, +2, +3, -1, so we are at +2. So once we get past 3.1, now we're at +2. Keep going, we hit the next pKa, which is 6, right? So we're going to have to draw the whole thing again, the same principle applies, we just lose another proton, so go to +1. So we're down to +1 here. We hit the next one, right? Which is, I'm going to call it 8.0. So we pass 8.0, we're at 0. And we pass the next one, 10.4. We're at -1, right? So there we go. The higher the pH, the more negative the charge. So at pH 4 then, now that we have this little thing drawn out, what is the charge in our tripeptide? Why? Yes, it is +2. Don't be embarrassed. So why? Very easy answer. Yes, in the back.
Because the terminal carboxyl is deprotonated.
pH 4, well, we're between pH 3.1 and 0.6, or between 3.1 and 6. So the most predominant will be the +2. Now, this isn't 100%, right? So we're not gonna have 100% of our tripeptides in solution be at the +2, but most of them will be in the +2 state, right? If you want to get fancy, you could use the Henderson-Hasselbalch and calculate what A minus over HA is, and then take a weighted average of the charges, right? But nobody's gonna do that, right? So instead we say that at pH 4, most of them are +2. Now what about the next question, right? What about at pH 8? Zero? Why 0?
The pH equals pKa, the terminal amine would have, or it would be like a buffer.
It would be at 50%, right? So could we say that it's 0? No. So we say it's +1? No. It'd be exactly half and half, right? By this point, all of these have already been deprotonated fully, right? But at pH 8, we're exactly in the middle. So I'm very sorry, this is a trick question. You could say it's 0.5, but that doesn't make sense. It's just 50% +1 and 50% 0, right? Now, what is the isoelectric point of this structure? First, who knows what the isoelectric point is? What does it mean? Is the point where what? It's the point where the peptide is neutral in charge. It's the point of what at which the peptide is neutral? Yeah, it's the pH at which the peptide is neutral, or when anything is neutral. That's the isoelectric point. So how do we calculate that? Well, calculating the isoelectric point means that we do have to put together this charge. You have to draw the structures, all right? Because all we care about is the charge. So here what we care about are the pKa values on either side of where the charge is 0, right? If we average those two together, we're gonna have 100%, we're gonna be right in the middle of this range. That's, right, that's what an average is. When we're right exactly in the middle of this range, we will be at 100% this, more or less, not exactly. Close enough to 100 to not make a difference, right? So what do? We take 8 plus 10.4, 18.4 divided by 2 is 9.2. So 9.2. That's the isoelectric point. It means that if we have a mixture of this tripeptide, we adjust the final pH of our solution to be 9.2, our peptide will have exactly zero charge on it. All right? Now, if to this we add 0.1 molar hydrochloric acid, right? What will the resulting pH be? Right? So say that we're at our isoelectric point and we add hydrochloric acid to a final pH, or a final concentration rather, of 0.1 molar. First, what kind of acid could we classify this as? Is it a strong acid or a weak acid? A strong acid would have a pKa close to 0, right? These are not close to 0. These are all weak acids. Each one of these protons are weakly ionized. So this we would say is a weak acid, right? So what equation do we need to calculate the pH of a weak acid solution? It's got a very funny name. Harry and the, no one knows Harry and the Hendersons. The there we go, the Henderson-Hasselbalch equation. Very good. pH equals pKa plus log A minus over HA, right? And we are here. Now, we're talking about acetic acid as our example on Tuesday. That was very easy. We only had one pKa. In this case, we have 4 pKa values. Which pKa value are we going to pick for our Henderson acid activation? If we're adding HCl to our zero charge state, right? Is the pH going to increase or decrease? Decrease. So we're going in this direction, right? So the reaction, the ionization reaction we're concerned with is this, right? So this is the pKa value that we're going to use here. 8 plus log A minus over HA equals our pH, right? Now, we are, I told you before, at the isoelectric point. So we're at 100% this, right? So what is A minus or HA going to be? First of all, is this A minus or is this HA? And what we're doing is adding HCl. Is this A minus or HA? Right, A minus, right? Because we're going to protonate that to HA. So let's just rewrite this as H minus and HA, right? And we have a 1 molar solution of that, right? So right now, pH equals 8 plus log A minus, which you say is 1 molar. And how much of this do we have right now? No. We're gonna be adding the 0.1 molar. But at the beginning, before we've added the acid, how much of this do we have? No, we have 1 of this. Right? If we were at the pKa, pH 8, then we would have equal amounts. Right? But because we're here, I told you a moment ago that we must have 100% this, and we don't have any of this. Right? Well, now we've broken something. Right? We're doing 1 over 0. When we're doing these problems, you have 2 approaches. Okay? You can do it the correct way, or you can do it the lazy way. Who wants to take a chance at the correct way? Right? So obviously this cannot be correct. This can't be it. Right? So what could we do to make it correct? Well, here we're solving for a pH that we already know. I told you we're at the isoelectric point, right? Make sense? Right. And we know that this can't be it. But we do know that we need to use this pKa. So, why don't we just solve for A minus over HA, right? So A minus over HA equals 10 up to the 9.2 minus 8, which is what? 1.2. Thank you. Right? And what does that come out to? Somebody calculator me. 10 up to the 1.2 is? Very much. 15.8. So now we can say that A minus over HA is 15.8. We don't know how much exactly A minus we have or how much HA we have at this point. Right? So what do? Well, we know that A minus plus HA must be equal to what? 1 molar, right? Because that's how much total we have. We can have either HA or A minus, so both we put together must be 1 molar. Right? So let's do a substitution here. Say that HA equals 1 molar minus A minus. Right? So we'll plug that back in over here to say, we don't really care about any of this right now. It's fine. So we can say that is that A minus over 1 molar minus A minus equals 15.8, right? So calculate that. minus equals 0.94, which means that HA should be 0.06, right? Which means that now, if we come back over here, now we know A minus is 0.94, 0.06 must be HA. This altogether will give us a pH of 9.2, which we know that we're at because I told you that we're at the isoelectric point, right? And this is where the laziness comes in. 0.94 is pretty close to 1. So that mistake that we made before, saying that 1 over 0, we can make that mistake because of this next step, right? So now we have everything all laid out here, and we're adding 0.1 molar to we're adding HCl to a final concentration of 0.1 molar. So what's going to happen now to A minus and HA? If we add 0.1 molar, is A minus going to go up or down? If we add HCl, rather, if we add HCl, is A minus going to increase or decrease? Decrease. Is HA going to increase or decrease? Decrease. By how much is A minus going to decrease? 0.1 molar, because HCl completely dissociates into H plus and Cl minus. All that H plus is available to turn A minus into HA, right? So we can say now that at equilibrium, when after we add the HCl, our pH will be 8 plus log 0.94 minus 0.1, which is 0.84, divided by 0.16, which comes out to what? A plus 8.7. Let's do a sanity check. We started at 9.2, we added HCl, and we're at 8.7. Does that make sense? Yes. Right? Very good. So that's how you do it the right way. Now, how you do it the wrong way, and the lazy way, is instead of figuring out what A minus is exactly, what HA is exactly, if we're working with enough acid, then it generally won't matter. Right? So if we say, okay, like I told you before, we have 1 molar A minus and 0 molar HA, and we add 0.1, right? Well, now we'll have 0.9, 0.1 molar HA, right? So if we do this conversion calculation, 9, now we get a pH of 8.95, right? It's not correct, but it's pretty close, right? So 8.7 is the actual correct answer. 8.95 is the correct enough answer, okay? Now, if we do the same thing for NaOH, right? Not going to go through that because it's exactly the same way, except that now we're looking at this over here, right? So we're using this pKa, this is HA, and this is A minus, right? Very good. All right, so let's see. Case study. So the case study really was about mad cow disease, bovine spongiform encephalopathy, right? I got a couple of minutes. And really the point to drive home is, this isn't just esoteric in what we're discussing, right? Protein structure and how proteins fold. It's very dry. Frankly, it's very boring. Yes, no one's enjoying a discussion about protein ordinary structure. But it does have real world implications, because what causes mad cow disease from the video? What causes it? Prions, right? And prions are so dangerous, right? Because they can't be treated, okay? In fact, you would think, for example, if I were to isolate a protein and inject it into any one of you, okay, that would elicit an immune response. You develop antibodies against that protein, and your body would be able to recognize it and destroy it. So, if you were to eat contaminated meat, or somehow else come into contact with a prion, why isn't the same thing the case, right? Your body should be able to recognize a foreign particle and mount a response, right? Well, why doesn't it? Well, it does, okay? In fact, it can recognize this foreign particle. It takes it into the dendritic cells in the immune system. And typically, when a foreign particle is taken in, endocytosed into the dendritic cells, it's sent to a lysosome. And the purpose of this lysosome is to use low pH, about stomach acid levels, so pH 1-ish, okay? And low pH denatures proteins, right? So this would destroy the protein entirely. It so happens that the structure, the misfolded structure that a prion adopts, renders it invulnerable to acidic hydrolysis, right, or to acidic denaturation. So it's resistant to that. It remains in the dendrite, in the dendritic cells. They can also try to destroy a protein via proteolysis, sending it to the proteasome, right? It's the second method that they have to protect against foreign agents. But prions are resistant to that as well. So prions remain in the dendritic cells functionally forever. And when they come into contact with other proteins, right, specifically major prion protein, it induces them to misfold, right? So how can this protein be misfolded if what I just told you is that the correctly folded state of a protein is its lowest energy state? It means that any other state must be a higher energy state. And that is true, right? If we think about prions, major prion protein, it does have a lowest energy state that is correctly folded and fully functional, the function of which is entirely known. But the misfolded state, right, the one that causes these prion diseases, is only marginally less stable. It's so marginally less stable that they can both effectively exist. Okay, one is preferred to exist both, functionally and thermodynamically, but the other one is so much less not stable that it can also exist. And when it does, right, it induces other proteins to also misfold, right? And why does this matter? Well, because now all of these prions are in the dendritic cells. And where do dendrites go? Where can they go? Well, they can cross the blood-brain barrier. And once they cross the blood-brain barrier, now these prions that are in the dendritic cells might come into contact with, again, major prion protein that are found in neurons, specifically in the synapses, right? And when these prions now come to contact with these major prion proteins that are correctly folded in the neurons, okay, well now we get degradation or misfolding of those proteins as well. Now, the function of this major prion protein isn't entirely known, but what is known is that the unfolded state, or the misfolded state rather, consists of mostly beta sheets, and they can stack on top of each other. And they can form these structures known as fibrils or as plaques. Right? We see this in Alzheimer's patients, right? So protein misfolding plays a part there, but in specifically prion disease, like in mad cow disease or bovine spongiform encephalopathy, right? What happens is that depending on where in the brain that dendrite ends up, right? If it ends up in one place, you might have certain symptoms, motor symptoms or memory symptoms similar to dementia, right? Because what's going on is basically these prion proteins that are correctly folded are then being induced to misfold specifically in neurons in that region of the brain, right? And the same is true for many neurodegenerative diseases, but they don't involve that prion protein. They do involve misfolding of real proteins, right? Again, in Alzheimer's, we get that misfolding that forms those plaques, right? We see those plaques in the brains of Alzheimer's patients, typically in the hippocampus, which is responsible for long-term memory, right? So that's one thing. We might find it in motor neurons, right? What disease might you expect to find misfolded protein aggregates that results in motor dysfunction? Parkinson's, right? So this is a family of diseases caused by protein misfolding, right? So it's not just something that happens automatically and everyone goes off happy. Serious diseases and very severe